Hey, good morning.
Good morning.
Morning.
Just 9 of us today. Okay, 10 with me. Okay, first of all, I'm just going to open the floor to questions. It would be unusual not to have questions at this point or concerns. All right, when you think of them, or when you want to ask them, just butt in. Also, on the discussion for the previous module, I noticed last night that people had actually asked some questions there, and I had gotten out of the habit of checking the discussion section, so I'll get back into the habit of checking the discussion section. If you have issues when you're doing your homework, you can ask those questions in the Module 4 discussion section, and then I'll keep an eye on it and try to answer in a timely fashion. It is helpful, since the homework's due Monday, that you don't ask the question Monday afternoon or Sunday night. I was pleased that students were responding to each other. That's good. That's what we hope for. Okay, I want to walk through these examples one more time and then go through the third example that the Cornell notes shows. In this case, they are prepending a 0 to a string. And if you think about how you want to do that, so they've got a string of 1s and 0s. They're going to prepend a 0 to the front. And the way they're going to prepend a 0 to the front is, I'm going to describe it this way. One way to do it would be to copy the whole string 1 space to the right in terms of the cells on the tape. Every 0 and 1 gets copied 1 to the right. And then you go back to the front and just write a 0 there at the very first position. That's how you can prepend a 0. They do it all at one time. They start out by putting a 0 at the front and then remembering what it was that they just wrote over, and then moving 1 to the right, and whatever they had before, a 0 or a 1, they put that in the cell to the right. But then they remember what they were looking at again, and they move 1 step to the right, put that there, remember what they overwrote, move 1 step to the right, and they do that all the way down to the end. At the very end, when they reach the big square cup, the end of the right-hand side end of string marker, they do not carry on and rewrite that on the right end of the string. They just leave the string open at the end. That's a little distasteful to me. I don't know. Kind of seems to me that there's some value in keeping the string format where you have the triangle on the left and the big square cup on the right. But that's a trivial difference. So if we look at this thing, they're describing that they have 3 states, R0, 4 states technically, the start state, and then R0, R1, and L. And R0 what just means that, hey, I'm moving to the right and I have to write a 0 next. I've seen a 0, so I have to write a 0 next. And R1 just means I'm moving to the right and I have to write a 1 next. Now, there's nothing magical about those names. They're clearly named to be mnemonic of what's happening, of what the action is. The important thing is stating the action. And then they go all the way back to the left and halt. Now, they could have halted technically if they're not going to do anything on the right-hand side. Once they've reached the end of the string, technically they've done that job, and so they don't have to go all the way back to the left. But that was just included. And then the machine halts. Notice, again, the finite state machine has 3 special states: halt, yes, and no. When you're doing a computation, you're going to end in a halt state. when you're asking a decision question is something that's answered with a yes or a no, then you would halt in either the yes state or the no state, which obviously you can correspond to true and false if you want. So do we have questions about how this machine works? Do we have questions about what I'm expecting in the homework for how you would explain how your machine works? Because I posted the homework and asked you to create 2 different Turing machines. I'm going to ask Michael, who's grading furiously, by the way. I know he just sent me an email about the homework 2 questions. He likes to grade them all and then put all the grades up at the same time. So he's almost done with homework 2. The questions about how you would, what I'm expecting. I'm going to ask him to be a fairly light-handed in grading these things. But the main thing you have to do is describe what your actions are. If you want to ascribe states names to those, that's great. If not, I'm not going to worry about that. Just describe what your machine does and what the action is going to be as you're moving left and right. And the examples I gave in these notes can give you a guide. My advice, as always, is to make life easy for the grader. And saying too much is better than saying too little. You might want to hand it to a friend and see if they know what the heck you're talking about. See if they can understand what machine you're describing. Okay, the second example. Now, by the way, if we can put a 0 in front of a string, do you agree we could also put a 1 in front of a string? In other words, we could shift the whole string to the right and stick a 1 in the front. I don't think I don't think that requires much argument, right? The choice of a 0 or a 1 are arbitrary. Now we're going to do the +1 function. And one of the things that you have to do, or one of the things that you can do, is be clever about how you're going to manipulate the strings to get the action done. You're allowed to do things like, okay, I need to just, in order to figure out what's going on with this string, I need to destroy it. Well, before you destroy it, you're allowed to make a copy of it off to the right-hand side. That way you have destroyed the original string, but you have a copy of the original string to work with. So if you're ever in a situation where you need to make sure of something before you actually start your action, you're allowed to make copies. That's okay. For example, let's say you wanted to make sure you had an even number of 1s in a string. In this case, you wouldn't necessarily make a copy, but think about ways you could do that. You could just walk through the string and keep flip-flopping between 2 states, even, odd, even, odd, even, odd. And when you're at the end of the string, you want to be in the state even. If you don't want to do that, you could off to the right start counting. Every time you see a 1, go to the right and start a new integer that just counts. It starts at 0 and then you add 1, and then you go back and look for the next one and you add 1, that kind of thing. In order to do that, you might need to destroy the first string because you have to keep track of where you left off when you go back. How are you going to do that? Well, usually you do that by actually disrupting the string. So be flexible in how you start to think about how things are done. Here we're adding 1 to a number. Now you've all learned how to add in binary math. And you all know how to add 1 in binary math. And the way you add 1 in binary math is if I have 1, 0, 0, 0, 1, 0, 0, 1, and I want to add 1 to that, I start from the right and I go to the left, right? I go, okay, I'm going to go, let's see, 1 and 1 is 0, carry the 1, And then from there you start, okay, I don't need to do anything else, so I'm going to copy the rest of the string down. But your intuition is to start from the right-hand side and add and then roll that thing through. But if you look at the final effect, you can think of it a different way, and that's what the author does. They take advantage of this notion that, wait a minute, if I'm going to add 1 to a number, 111000, it's 111001. Or if I do 100111, it's going to end up being 10010100. Oh, okay. Well, if you notice that pattern, what's really happening is you're taking the rightmost 0 and changing it to a 1, and then all of the ones behind the rightmost 0 got flipped to a 0. And if you think of adding 1 that way, then you don't have to deal with the actual adding of every single integer space. By that I mean when you learned how to do binary math, you learned how to add 1 and 1 is 0, carry the 1, 0, 0 with a 1 carried is 1, 0, 0 plus, right, 0 plus 0 is 0, 1 plus 0 is 1, da, 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 and you went from right to left, and you did all of those, computations. But the end result was you took the rightmost 0 and flipped it to a 1, and then if there were any 1s behind it, you flip those to 0, and that's what the author's taking advantage of here. So what does the author do? First of all, let's ignore the case where you don't have any zeros. What the author does, he goes all the way to the right, and then he goes, once he hits the end of marker, the right-hand side end of marker symbol, he starts going back to the left, and as long as they keep seeing 1s, they're flipping them to 0s. And if they keep flipping them to, if they keep flipping all the 1s to 0s, eventually they'll hit a 0, they'll flip it to a 1, and then they're done. Basically, he does this trick where he goes back into that left state and just slides back to the left, back to the left-hand side of the string marker. Like you've seen printers in action. After they're done printing, they all just reset back to their original state. That's all they're doing. The only thing that can go wrong is they are moving left and they are keep flipping the 1s to 0s, keep flipping the 1s to 0s, keep flipping the 1s to 0s. And the only thing that can be wrong is you never find a 0. So if you never find a 0, you'll find the end of string marker on the left-hand side, and you recognize that you haven't found a 0. And therefore, you can say, uh-oh, I need to add a 1 in front of this. Well, we've already proven that we can prepend a string with a 0. Therefore, we can prepend a string with a 1. And so that's what's happening down here is they do the prepend a string with a 1. And basically what's happening down here, if you look, this prepend SRL is basically the same machine as we had in the previous example. Because all it's doing is shifting all the zeros to the right one space after it put a 1 in the front. So part of the trick of building when you're designing your own Turing machine, again, and this is just a theoretical exercise, you're not going to do it in real life, but part of the trick is noticing the patterns in computation sometimes and taking advantage of those. Hopefully by now you guys have gotten familiar through your programming experience with instructing a machine that has no brain on how to do stuff. And again, that's what you're doing. This is a machine with no brain. How do you instruct it to do something? When we give instructions or when we think of how something's going to be done, we often act as if the thing has a brain because that's how we're used to doing things. And I see that in a lot of you, I think all of you have taken CS332 with me. I see that in CS332 a lot because people are going to describe what they want their software to do for their project. I want it to do this, I want it to do that. You know, my question is always, okay, great. How are you going to make that happen? So that's my advice as you're working on your problems. I would look at them today, so you have a while to think about them. And think about, okay, how would I do this on a mindless machine? In the problems, the two problems that I gave you, I am using, you know, normal digital binary numbers like the Cornell notes use. Let's see, the Cornell notes use also then the, let's go through here. The third example is to subtract 1. Not sure why I didn't put it in the notes, I just didn't. So we have subtract 1. Now if you think about how you subtract 1, do that same trick in terms of patterns. How do you subtract 1? Let's see, assume, let's get rid of this case right off the bat. How do you subtract 1? Oh, you need a way to represent negative numbers on the Turing machine tape, and the author just says right out, we are not doing that. 0 minus 1 is 0. So now the other case is, what happens if you have a 1 in there? So let's see. Let's keep small numbers. 1. If I subtract 1, it's going to be 0, 0, 0, 0. Right? What about 0, 0, 0, whoops, 0, 0, 0, 1, 0? If I subtract 1, that's going to be 0, 0, 0, 0, 0, 1. And if I do 0, 1, 1, 0, 1, 0, it's 0, 1, 1, 0, 0, 1. 1, 1, 1, 1, 0, 0, 0 is going to be 1, 1, 1, 0, 1, 1, 1. Do you see the pattern? What's the pattern here?
You're taking the rightmost one, turning it to a 0, then all the zeros behind it are turning into 1s, if I'm seeing that correctly.
Right, right. And hopefully that makes intuitive sense to you. Yeah, hopefully that makes intuitive sense. Because what did we do when we added 1? We took the rightmost 0 and changed it to a 1, and we took all the preceding 1s and changed them to a 0. Now we're taking the rightmost 1 and changing it to a 0, and taking all the zeros after that and changing it to a 1. In other words, we're doing the exact opposite. Well, isn't minus 1 the exact opposite of plus 1? And aren't these reversible functions? So what we're doing are the reverse actions. So hopefully just intuitively that makes sense to you. So the author is going to ignore the case where they have all zeros, just going to return a 0. And otherwise, the author will do like they did before. They go all the way to the right, then they start coming left. And as they come left, as long as they see zeros, they're going to turn them into a 1. And if they see a 1, the first one, they're going to turn it into a 0. And then they just continue on to the left until they see the end of string marker and they're done. Now these states, again, they're named Z, R, L, and T, you know, not very descriptive names. So no, the mnemonic is not so great there, but R and L, they're typically talking about left and right. T is, I think they're using that to indicate they've got a good, you know, a non-pathological case here. In the case of addition, the pathological case was that you effectively had overflow and you had to prepend a 1 to the front. And in the case of subtraction, the pathological case is you have all zeros and they're ignoring those. So again, we can walk through this and see that they're just going to go to the right. That's what the Z state is they're going to the right. And all they're doing is copying what they see. If they see a 0, they're going to put a 0 back. If they see a 1, they're going to put a 1 back. If they see the end of file marker, they're going to put it back. But now they're going to start going to the left. And the fact that they've seen, let's see, then they go into T, and in T they're going to the left, and if they see a 0, they keep a 0. Where are they flipping these things? S goes to Z, and then Z goes to 1, this goes 0. Oh, I see. I see. With Z, when they go to 1, that's when they go to state R, which is to say, hey, I've seen at least 1, 1. Otherwise, if they stay in state Z and they see zeros, they stay in state Z. And that's why if they get to Z, big square cut marker, that's where they say, okay, I have not seen a 1. This must be a string of all zeros. Therefore, I'm just going to ignore the computation and go back to the left-hand marker and halt. But if they ever see a 1, Z1, they go to state R, and then state R continues, because they're still moving to the right, they continue moving right, just copying over what they see. And then finally, when they get to end of file marker, they go left. And look what left does. If you see a 0, keep going left, but replace it with a 1, and keep doing that until you finally see a 1, replace it with a 0, go to state T, which is basically moving without changing anything, and then halt. In the way, now if you want to include this table in your answer, that's great. I'm not requiring that. But a verbal or a narrative description sufficient for the grader to understand what you're doing. You might want to start out ahead of time with the kind of discussion I just had. You know, hey, here's how I know how to do this. Here's the pattern I'm noticing. And so now I'm going to make a machine to do that. You know, give a good common sense description of what you're trying to achieve is my advice. And again, if you want to include that, that's great. That's actually the best way to do it. All right, it's a non-ambiguous deterministic definition of the machine. Okay, once we have this under our belt, we can start to talk in more fuzzy ways about how a machine works. Now here I'm changing the encoding scheme. I'm encoding the numbers as just sequences of zeros, and I separate these numbers with the number one, with the numeral 1. So 3 zeros in a row is the number 3, and then the 1 is telling me I'm coming up to a new number, and 2 zeros in a row is the number 2, and then 5 zeros in the row is number 5. And what I'm doing is I want that string to represent 3 plus 2 equals 5, and I want to verify that I have a correct addition equation. So all I have to do is I start at the left-hand side in the start state. I traverse to the right, copying over the string. I don't change the string. And then I see the 1, and I just remove the 1. Then I go back to the left-hand side, and I start to the right, remove a 0. Now, let's see. Once I remove that 1, let's do that first string. I can't do the triangle in Notepad. I'll do that. I've got 3 plus 2, plus 2 equals 5, and the file marker. And I'm saying the first thing I'm going to do is go remove the 1. And then the next thing I'm going to do is go to the right and remove the first 0. Keep going to the right until I see the 1 and remove the first 0. And I'm going to keep doing that. Now I go all the way to the left. I could go remove it on the way back, but I'm not going to. I go all the way to the left and repeat that again. Remove the first 0, there's the 1, remove the first 0, go all the way to the left, do it again. Go all the way to the left, do it again. And if I end up with that string, then I'll halt. So if I go all the way to the left and all I've done is seen the 1, 1 and then end of file marker, then I halt and I say, yes, this is a good, good result. So I'm going to use the yes and no states here because I'm asking the question, is this string in the language? So I would say yes. Notice how remarkably inefficient that is, traversing back and forth and back and forth and back and forth. That's okay. We don't care about efficiency yet. All we care about is, can this be done or not? If I ever do end up with a string like this, or a string like this, then they are not equal. It is not a string in the language. And then I can recognize that and reject and say no. Now, I haven't written my table out for my machine, but is it clear what my machine does? Do you understand what my machine does? That's the question. You want to be able to get that understanding to the grader based on your Here I'm doing addition. Instead of just recognizing addition, I'm doing addition. Now I'm doing it again with the worst representation of numbers possible, which is each number is represented by the number of zeros that are in there. And here addition is trivial. If this string represents 1 plus 4, and this string represents 3 plus 0, and this string represents 2 plus 2, all I have to do is go and remove that 1. There's the answer. So we're having not just the ability to do answer the recognition question of the language, we're doing computation. And once you have +1, by the way, and in the authors, +1 is much, I'm sorry, the Cornell notes +1 is much better than mine because it's actually binary integers. Once you have +1, you know, you have all of mathematics. You can do it. You wouldn't want to write the Turing machine for it, but you can do it. All right, so that's how these machines operate. That's how they work. Finally, we have something that can represent computation. And then the question is, so what? What can we do about it? Okay. I'll be honest with you guys, days are running together. I don't think we covered the proofs yet in the discussion of what Turing machines can do. I don't think we did that on Monday. Is that a true statement?
Yeah, we didn't get to this point.
Okay, all right. Okay, good. Okay, so here's the thing. So once Turing developed this notion of a computer prior to computers actually being invented, the question, of course, was, so what can they do? If we ever do invent a computer, what can they do? And so the idea here is we have, you know, the idea that there are non-computable problems. Now, there are some non-computable problems that are fairly trivial. For example, the lottery question, right? What are the lottery numbers going to be next week? Well, you know, predicting the future is not computable. That's understood. But what if you have situations where you can actually write an algorithm for something? Then the question is, are all problems that you can write an algorithm for computable? And there's a couple of big results that come out of this. And they're just as valid today as they were in the 30s. And the bottom line is no. And you can do this, you know, I'm not going to do a formal proof, but I'll do a proof sketch, and it's a contradiction proof. You know, whenever you have to prove that something cannot be done, the contradiction proof is usually the way to go. So it's a contradiction proof. You assume, again, remember what a contradiction proof does, you assume the opposite. So let's assume all problems are computable. Then we'll have a set of Turing machines. And the Turing machines must represent all problems, because if all problems are computable, then the set of all Turing machines would cover all the problems. Each Turing machine solves a specific problem. And since all the problems are computable, there are no Turing machines outside of the set of S. Now here's the trick. It's called a diagonalization proof, and technically it's called Cantor's diagonalization proof, because Cantor's the guy, I think, that first developed it. What we're going to do is create a machine that's outside of S, and there becomes the contradiction. You know, right? There are no machines outside of S. Oh, here's a machine outside of S. There's your contradiction. Now, one thing to think about is Turing machines. Here's the table, right? What if I took each row of that table, and instead of writing those rows one below the other, I wrote those rows one after the other? Now what do I have? I have a string. So I can represent a Turing machine as a string, and that's going to become critical in the next section too, the next part of the discussion. I can represent a Turing machine as a string. So if I represent a Turing machine as a string, then the way I create my Turing machine that's not in the set S is I take whatever the symbol is for the first symbol of the first Turing machine, I'm going to flip it. So if it's a 0, I'm going to let it be a 1. It's a 1, I'm going to make it a 0. And then I'm going to do that for the second position of the second machine, and the third position of the third machine, and the fourth position of the fourth machine, and so on and so on. And if you think of these machines all laid out in an array, what you're doing is you're changing the diagonal. And that's why it's called the diagonalization proof. Now I've got a machine M prime that cannot be the same as M1 because it's different in the first position, and it cannot be the same as M2 because it's different in the second position, and it cannot be the same as M3 because it's different in the third position, on and on down the list. So basically M prime is going to be different from every machine that's listed in S. In other words, M prime is not in S, which tells you that there are, because each machine corresponds to a problem, there are problems out there that cannot be computed. Now, we kind of knew this, right? I mean, other than the predict the future problem, hopefully you already knew that. It should not be an earth-shattering result, but it's an actual formal proof of the result. Notice it doesn't talk about what kinds of problems are not computable yet. So the next part of the discussion actually talks about the kinds of problems that are computable and not computable. And first, let's talk about what makes something computable. Termination. Something is computable. If I ask a machine a question, yes or no, then I have to be able to have that machine terminate and actually give me a yes or give me a no. If it doesn't terminate ever, then I don't have a guarantee of a result, which means I don't have a guarantee of computation being completed. So not everything is guaranteed to terminate. So for example, for the robot problem, you know, this is a nice intuitive way to think about non-termination. You do a simple problem. We've got a wall, and you know, we start at the starting point of the wall, and the wall goes infinitely in one direction. Let's let it go west. And you start the robot over in, you know, Boston on the East Coast, and you say, okay, go find the door. There's a door in the wall. Go find the door. And the wall is infinite. Are you guaranteed that that robot will eventually find the door? Is that a guaranteed problem for termination? And the answer is yes. We don't know when it will terminate, but since there is a door in the wall, and the door must be a finite, even though the wall is infinite, the door is a finite distance from the starting point, then the robot will eventually reach the door and say, found it, and terminate. By the way, that's one way to think of infinity. Don't think of infinity as, oh, it's infinite, it takes forever. Think of infinite as you have potentially a number without bound. So we won't put a bound on where the door is, but once you put that door in the wall, that's a finite distance. We just didn't say ahead of time that it has to be bounded by some number. But once it's there, it's a finite number, and therefore the robot will find the door. Now let's change the problem slightly. Start the robot out and say, we don't know if there's a door in this wall. Tell us if there's a door in this wall. And now the robot, if it does find the door, can definitely answer yes. If it does not find the door, it can't stop, because what does it really mean? It hasn't found the door yet. And so it can never answer no. It's just not yet. So the idea here with the second version of the robot problem is the notion that you can construct fairly trivially problems that have no guarantee of termination. So we have this notion of decidability. Okay, decidability means I decided something, yes or no. Is there a door in the wall? You decide, yes or no. I can decide yes, but if it's an infinite wall and I'm asking you if the door is in there, I can never decide no. Let me relate that back to the grammars for a minute. So if we go back to the grammars and say, oh, now the grammar, remember unrestricted grammar had the property that you could reduce the terminals in the string. And remember that the Turing machine corresponds to the unrestricted grammar. So I gave you, it's in the homework, right? The Moo puzzle. The Moo puzzle has certain rules, and some of those rules remove terminals from the string. So you start with the Moo puzzle with MI, and there's a Backus-Naur form grammar, and you're trying to derive the string MU. So if you start with MI, can you produce MU? And it's hard to figure out because some of the rules actually remove portions of the string, which means you can make the string longer and then make it shorter, and then make it longer and then make it shorter. And it might be that you can solve the Moo puzzle, but you have to first make that string 100 symbols long before you reduce it back to Moo. Oh, okay, 100 didn't work. Maybe 500 will work. Oh, that didn't work. Maybe 1,000 will work. Oh, that didn't work. How about 1,000,000? You know, how long can I do this game? Basically, what you're saying is you don't know if there's a magical number out there somewhere where the length of the string will finally collapse back down to mu, and therefore, if you're just brute forcing the mu puzzle, there's no guarantee of termination. And this is completely different from the other languages, because if you remember in the, let's specifically focus on the regular and the context-free languages, you couldn't destroy any of the terminals, which meant if you ask the decision question, is this string in the language? One way to do that is to just use the derivation rules and derive all possible strings of length. Let's say the string was of length 5. You can derive all possible strings of length 5 and see if one of them is the string that you're looking at. And if your string was of length 10, you could derive all possible strings of length 10 and then see if your string is in that set. So you can brute force the answer and guarantee termination using the regular and the context-free languages. But since the unrestricted languages allow you to demolish the terminals, you can't say I'm going to brute force my way of all the strings of length. In this case, strings of length 2. I can't brute force my way to create all strings of length 2 because I have to first make the string larger and then smaller and larger and smaller, and there's no upper bound on what larger means. So the mu puzzle, if there's a no answer, if you cannot derive mu from mi, there's no termination to the quest if you're doing it by brute force. If you can, you'll find it and you'll get the result. But if not, there's no termination. By the way, you cannot create mu from mi, and it's a induction proof that proves that. And you can find it online. That's why I didn't ask anybody to try to do that and determine the answer, because it's online. All right, so let's take this same idea of termination, and it goes, Turing addressed it directly, the halting problem. And here's how the halting problem is framed. Remember I said we can take a Turing machine and we can represent it as a string? That's what we did in the diagonalization proof, to prove that there are some problems that are out there that are not computable. And it really hinges on termination. So Turing said, well, heck, let's talk about the termination problem. The halting problem takes this form. I'm going to represent a Turing machine as a string. I could print that string on a tape. Here's where things get weird. I could give that tape to another Turing machine. If a Turing machine is nothing but a sequence of symbols on a tape, and a Turing machine can do computations of sequences of symbols on a tape, which we've seen, we've done the add 1, we've done the -1, then I'm going to take a Turing machine that analyzes other Turing machines. And the development of this idea and the actual details of the process are beyond the scope of the course, so just trust me, right? Trust me. But you can create something called a universal Turing machine. And what a universal Turing machine does is you put a Turing machine and you represent it as a string on a tape. You give that tape to the second machine, which is the universal Turing machine. And then that universal Turing machine will simulate the first one. In other words, the Turing machines are programmable. And remember, I keep saying there's a correspondence between Turing machines and real-world computers. Even though the Turing machine is such a clunky device, there is a correspondence between it and real-world computers. That's one of the correspondences. Do you agree that you can program your computer to change its behavior? Hopefully you do. You've done it. So it's the same thing. The Turing machine is not only a universal computational device because it can be programmed. So then we say, okay, let's take in the Turing machine and the universal Turing machine. And here's the question we're going to ask the universal Turing machine. It's another decision question. It's another yes and no. And we're going to give it one string to represent a Turing machine and another string to represent a problem. I'm going to change that slightly in a second, by the way. A Turing machine and a problem. And we ask the universal Turing machine, will this Turing machine that I just gave you halt on this problem P? And then it answers yes or no. Is it guaranteed to halt on problem P? Now we can take the problem P away and say, I'm just going to give you a Turing machine and ask you the question, hey, universal Turing machine, I'm going to give you this Turing machine and ask you the question, is this Turing machine guaranteed to halt for all problems I could possibly give it? You know, all instances of the problem. Remember, Turing machines are built to solve one problem, right? So it's not any problem, but any instance of the problem or any example of the problem. Like addition, the Turing machine that I did earlier for that stupid way to do addition, will it halt for all possible legal inputs? The answer is yes. When the Cornell notes did the +1, will that machine halt for all possible legal inputs? The answer is yes. And you know that because you did the logic external to the system. You looked at that machine as an external entity and did some analysis in your head. But now we're not asking an external entity, we're asking the Turing machine to answer the question. Is M guaranteed to halt on problem P, or is M guaranteed to halt on all possible instances of problem P? And then you ask that universal Turing machine, and it's a decision problem, yes or no, and it's provably undecidable. And there's two mechanisms to prove that. One is diagonalization proof. That's not the most popular way. The most popular way is to set up another form of contradiction. Remember, whenever there's a no answer, it's contradiction. And the contradiction I always found to be kind of weird, so I didn't present it here. It is presented in the Cornell notes if you want to go through it. But basically what you do is you create a Turing machine that if you create the contradiction that says, if that Turing machine that I fed you will halt on all possible inputs, you're going to answer no. And if it won't halt on all possible inputs, you're going to answer yes, and that sets up a contradiction. I'm going to completely ignoring those details. Okay, so let's talk about what that means for a minute. So we have this notion of, okay, decidability in Turing machines. We've proven that not all problems are decidable and computable, and we've proven that the halting problem specifically, or at least we've discussed that the halting problem specifically is one where a universal Turing machine cannot answer the question, will this Turing machine halt all the time? And so why do we care about that? Because these are just Turing machines, right? Okay, instead, think software. Think about software. If the first Turing machine was really a piece of software, and it is, what we're asking the universal Turing machine, which is another piece of software, what we're asking is, hey, universal Turing machine, you are software, and your job is to analyze another piece of software and to give us the answer, will it always terminate, yes or no? That's your job. And the answer to that, question of, hey, that's your job, is I can't do that job. I can never give you a definitive answer about the question. So if you wanted to build software and your software's job was to take in other people's software and guarantee termination all the time, your software cannot be built. It's provably not doable. You cannot write software to analyze other software to see if that other software will halt. Now you can in restricted cases, we're talking about in the general case, the generic case. In restricted cases, yes, you can. You make sure all the loops have constants in them or something trivial like that. But in the general case, you cannot. And this is a big deal. Why is it a big deal? Well, first of all, have you guys ever worked with software that analyzed other software? Has anybody ever done that here? Okay, everybody has done that here. How many of you guys have ever used Eclipse and while you were typing, Eclipse told you had a syntax error? Anybody?
I have, for sure.
Yeah, everybody has. Everybody has. Well, what's Eclipse doing? It's analyzing your software. Yes, that counts. That counts, yep. You've used Eclipse, and Eclipse has analyzed your software. And how many of you have had, once you try to compile an Eclipse, a compilation error because it said, oh, this type doesn't match, or you can't reference a static entity from a non-static reference? Oh, that's software analyzing software. So it is commonly done. Now, there are more sophisticated pieces of software out there. There really are pieces of software that analyze other softwares and try to help you do debugging, like, program. They create things called program slices that say, okay, here's statement number 412, and I'm going to find all the previous statements that could potentially affect program statement 412. Oh, and then I can also find all statements that could potentially be affected after statement 412 by statement 412. Those kinds of software really do exist. Those are the kinds of things that are decidable. A syntax error is decidable. We can find it. And if there isn't one, we can answer no. If there is one, we can answer yes. So we get a definite yes, no answer. But to ask harder questions like, is this a virus? Why isn't there software out there that instead of, how does software, think about how virus software matching works. You have a library of known known virus patterns, and your virus checker compares against the known patterns, and that's why every now and then, if you don't upload your patterns, it says, you're out of date. Would you like me to upload the latest patterns? It's pattern matching. This is finite state machine level recognition, not Turing machine level. But no software can literally analyze the actions of another piece of software and say, in the general case, this is a virus. That's why we have viruses. And I'm not going to ask you this semester, but I tend to ask during previous semesters the question, particularly of you software engineers, can you prove, based on your software engineering experience and training, can you basically provide real-world evidence that the halting problem, is real, and that you cannot create software to analyze other software? And it's a one-word answer. Does anybody have a thought on that? How do you know? If I could create software to analyze your software, how would that change software engineering? How many of you guys have spent a lot of time developing test requirements? Or any time developing test requirements? And you spend a fair amount of time in your courses talking about test requirements. Why do you have to test software? Tests are highly specific though, right, Casey? But instead of testing your software, if I have a set of requirements, why don't I just write another piece of software that looks at your software and says, yes, these requirements have all been met, or no, they have not been met? Why do I have to go through the testing process? Because it's impossible to do that. And the halting problem tells us that. For example, what you can do with the halting problem is map it to other problems. Let's, instead of ask, will this program halt, let's ask if this program will ever print. Well, what you can do is go through the program, and every time there's a print statement, you put halt after it, and now you've got the halting problem, because as soon as it prints, it will halt, right? So now we've got the halting problem. And the same thing with requirements. If I have 100 requirements, why can't I go through the program, do the analysis, and every time a requirement is met, I say halt? Oh, now I've mapped this to the halting problem, which is provably not doing it. How would you test the program that tests your original program? By more testing. It's a recursive nightmare. So you can't prove that your test program is correct. You have to test your test program. So this has real world implications. We can't detect viruses. We can't prove that our programs are correct through analysis. We can do it in a limited way, okay? And that's the trick. If you ever get into a situation where your employer is asking you to do this, remember that your employer is asking you to do the impossible unless there are very, very clear limitations, and then you have to convince yourself that those limitations make sense. If you have a program with loops, and those loops I can scan through, and it's always a constant upper bound, and it's always the exact same increment, I++, then I can confidently write a program that will predict that, yes, you have a program that will terminate. But if I can't answer those questions, I can't necessarily say no. I can't say no, it won't terminate. I just have to say I don't know. I don't have the capability to know that. Okay. Think about that stuff. We're out of time. Friday, I'm going to have office hours. I think we've covered the lecture material sufficiently. I'm going to have office hours. If you have questions, throw them in that discussion section, please. And we can kick it around. All right, guys. Have a great day.